let's talk about relativistic Lagrangian and then correspondingly the relativistic Hamiltonian, right? So we know that for a classical system, the Lagrangian can be written as the difference of the kinetic and potential energy, right? Okay, so now the question is that is this Lagrangian, that is for the classical mechanics, work for a relativistic system as well? Well, to answer this question, the best way to do that is to obviously work it out. So, well, for a relativistic system, the Newton's laws are written as follows. So, we have the proper time derivative of the momentum coordinate is equal to 0, right? But now we know that from the video on my proper time and proper velocity, I defined proper time as d tau is equal to 1 over gamma times the differential element of ordinary time, right? So gamma over here is our usual Lorentz factor. Okay, so with this definition, then I can write down this equation as gamma times the ordinary time derivative of my momentum coordinate is equal to 0. Right. So now the question is that how do I solve this system, right? So for the relativistic system, we will still use an action principle. However, of course, to be in accordance with the special relativity, some of the things must change, right? So, number one, in classical mechanics, the time t has been treated as a special coordinate, right? So, it is different from the spatial coordinates that are x, y, and z. However, we know that in relativity, space and time must be treated on an equal footing. By the way, which at first sounds weird, right? But if you think about it in such a way that one may say that, for example, she is 10 minutes away from, say, a parlor, right? So in a way, she is describing or telling about her distance, right? So it's a pretty rough example, but I hope you get the point, right? Okay, so getting back, that means that we must replace t, that is the ordinary time, in the definition of action by such a parameter which is Lorentz invariant and also traces the position of the particle in the configuration space. Now, obviously, a very good and a suitable candidate for this is the proper time of the particle, that is tau, right? Okay, so number two then is that the physics obviously must remain the same in all inertial frames, and so the Euler's equations. And the Lagrangian must be Lorentz invariant, which obviously implies that the action must be Lorentz invariant. Right. Now let's talk about the action of a relativistic point particle and recall from non-relativistic mechanics that the action can be or is written as the time integral of my Lagrangian, right? Okay, so just for some ordinary purposes, let's check the dimensions of this action, right? So we know that the dimensions of Lagrangian would be of energy, right? If you look at the Lagrangian over here, and so then we have this t. So the dimensions of my action then is energy times the time. Okay, so the action for, let me actually go on the next page. So the action for a non-relativistic free particle is we know written as this nr is for non-relativistic is equal to the time integral of the Lagrangian. Okay, but we know that we're talking about a free particle, so the Lagrangian for that particle is written as half mx dot squared, right? And this x is a function of time, right? Okay, so this is actually half mv squared, your usual kinetic energy. Okay, so with that then I can write my action for a non-relativistic particle as half times the integral of mx dot, which is a function of time, squared, right, and dt, of course, right? So I used this definition for action to write this expression. Okay, now my goal is to construct the action for a relativistic point particle with an assumption of a free particle. So I'm going to assume that this relativistic particle is a non-interacting particle, and so there would be no interaction term in its Lagrangian, right? Okay, so also note that the action must be Lorentz invariant, as we discussed earlier. So we start with a guess that we can write the action for a relativistic point particle as this expression over here, which is the original expression for my action, right? So this equation. Okay, so we know, or we just figured out, that the dimensions for my action are of energy into time, right? So for a relativistic particle, that would be energy into proper time, right? Okay, but we know again from the video on proper time and velocity, I discussed the space-time separation or the invariant quantity as ds is equal to c d tau, where ds is the space-time separation, c is the speed of light, and d tau is the differential element of proper time, right? Okay, so I should also mention here not to confuse this with the action s, right? Okay, now using this expression and this expression for action, I can then write down my action as s, which is the action, is equal to mc squared times ds, where this ds is the space-time separation, over c, right? Again, I just used this expression for action, right, this one, and I substituted for d tau from this expression over here in this, right? Okay, so well, then this is obviously equal to the integral mc ds, where ds again is the space-time separation. Okay, so from now here I'm going to make a claim, right? And I'm going to say that the correct action for my relativistic system is going to be the negative integral of mc ds. And the reason for this negative sign over here will be cleared at the end when I derive the Lagrangian, right? And so this negative sign is going to help me to remain inconsistent for my classical Lagrangian, right? So to remain consistent with classical Lagrangian for my speeds that are smaller than c. c is obviously the speed of light, right? So we also know that ds, which is the space-time separation, can be written as g mu nu in tensors as g mu nu dx mu and dx nu, right? And so I actually wrote this again in my video on the proper time and proper velocity. Right. Okay. So with this, I can then also write my action as the negative integral, or actually let me write MC outside the integral because they're constants, and integral G mu nu dx mu dx nu. So I have just substituted in ds with this. Right. Okay. Okay, so we wrote that ds, that is the space-time separation, is c d tau, right? Where again d tau is the proper time, and I can substitute for d tau as dt over gamma. Okay, so this thing is then equal to obviously c dt times the square root of 1 minus v squared over c squared, which is this 1 over gamma. It is the square root 1 minus v squared over c squared. And so with this then, if I substitute this ds in my action over here, right, what do I get? I get action is equal to negative mc squared times the time integral of under the root 1 minus v squared over c squared, which is again this quantity. I substituted for ds. Right. Now, if you look at this action, right, it is obvious to see from here what the Lagrangian would be, right? Obviously, keeping in mind that the general equation for action is the integral of my Lagrangian times dt, or the time integral of Lagrangian. And so if I compare this equation with this equation or expression, I get my Lagrangian as the negative mc squared times the square root 1 minus v squared over c squared. And so this equation over here is the relativistic Lagrangian, right? So let me just box it in. Now the next task would be, or a clever task would be, to find the Lagrangian for particles with speed that is much smaller than the speed of light. Right? And so, of course, if we get the correct classical Lagrangian, that means that our claim for the action that we made earlier was indeed correct. Okay, so let's go on and do that. So we are going to find the Lagrangian for speeds that are smaller than c. Right. Okay, so note that this equation for Lagrangian over here, the term in the square root can be expanded in terms of the binomial expansion, right? Using the binomial expansion, I can expand that and write it down as my Lagrangian is equal to negative mc squared 1 minus v squared over c squared to the power 1/2, right? And so let me apply binomial expansion on this term over here, and what I get is negative mc squared times 1 minus 1/2 v squared over c squared. Right. And I can ignore the higher order terms, obviously, because of this condition over here. Right? So obviously, if we include the higher order terms as well, it would converge to this Lagrangian over here that we have over here, right? Okay, so right now, if I open this term over here, what do I get? Let's see, right? What I get is my negative mc squared plus 1/2 times m v squared over c squared times c squared, right? So this c squared, and so then these c squared cancel out, and finally I am left with negative mc squared plus 1/2 mv squared. Now, if you note in this equation that we have this term, that is the kinetic energy term, which is what we should have for a classical free particle, so no potential, right? But we also have this term that is negative mc squared, and we know that from the Einstein's relation that mc squared is nothing but the rest mass energy for a particle. Now, it looks like that this negative mc squared is troublesome in this expression over here, right? But if you think about it, it is just a constant, right? So m is constant and c squared or c is constant. So which will then have no effect on the equations of motion, right? And that is obviously because the derivative would vanish, right? And so this would have no effect, and so it doesn't really matter if when we want to compute the equations of motions from the Euler-Lagrange equation, right? So we can then obviously ignore this term, that is negative mc squared, and write our Lagrangian directly as half mv squared. Right? I hope that why are we ignoring this negative mc squared is clear to you now, right? Okay. So the leading term, that is the half mv squared in the Lagrangian, then obviously coincides with the non-relativistic Lagrangian. And I hope that now you see the significance of us writing this negative sign over here for the action, right? Or where did we define it? We said that we will, or we claimed that our action is this thing, that is negative mc ds, right? So we added that negative sign, and we saw that to get the classical Lagrangian correct, that negative sign was important. Okay, right. So we are now essentially done with the Lagrangian for a relativistic system. Now the next task should be to work out the correct Hamiltonian for a relativistic particle. And so you could recall from classical mechanics that the Hamiltonian for a particle is written as the dot product of momentum and velocity vector minus the Lagrangian. Right. But we know then that the Lagrangian is simply equal to negative mc squared times under the root 1 minus v squared over c squared. This, of course, is the relativistic Lagrangian that we just derived. Right. Now, again, we know again from classical mechanics that the momentum is simply defined as the velocity derivative of the Lagrangian. So what would that be, right? So let's compute the velocity derivative for this Lagrangian. That would simply be negative mc squared over 2, right? So this half would come down, and we have over 2, and we would have 1 minus v squared over c squared. 1 by 2 minus 1 is negative 1/2, and the derivative of the inside quantity would be negative 2v over c squared. Right. Okay, so now you see from here that these two cancel out, negative and negative becomes positive, and the c squared goes with this c squared, and so what we are left with is then the momentum for a relativistic particle is defined as m times the velocity vector over under the root 1 minus v squared over c squared, right? And you could write this down as simply gamma times mv, right? And so this here is the momentum for a relativistic particle, right? Okay, so now the next task would obviously be to put this momentum in this equation for Hamiltonian over here. So let's go ahead and do that on the next page. Right, so the Hamiltonian would now be written as mv dot v, right? And so these are vectors over under the root 1 minus v squared over c squared, and the Lagrangian was then mc squared under the root 1 minus v squared over c squared, right? And so if you simplify this equation, and you get Hamiltonian as mc squared over under the root 1 minus v squared over c squared. And so this over here is your corrected Hamiltonian for the relativistic system. And this equation for Hamiltonian also coincides with the relativistic energy of the particle, right? Which you could derive from this relativistic momentum over here, right? Okay, so hence we recovered the familiar physics of a relativistic particle from the action that we claimed earlier, which, let me write it down over here again, was S is equal to negative mc squared times the time integral initial time to some final time dt. Now remember that this t over here is the ordinary time, and we have under the root 1 minus v squared over c squared. Okay, so note that this action is extremely elegant in physics and clearly Lorentz invariant, right? Okay, so now let's go a step further and look at the principle of least action for a relativistic system, right? So let me first quickly draw the graph, right? So let me just do that quickly. I would have on my vertical axis my time, and on my horizontal axis my space. So that is the usual convention for a space-time diagram. And then let's say we have some initial starting point and some final point, right? And so say this is the trajectory or the path that a particle takes, right? So initially what we have that the position coordinate at some initial proper time ti, and we have its initial velocity, right, mu at some initial time t tau I, right? And likewise we would have over here for the final x mu, this is the position coordinate at some final time, and its velocity, the particle's velocity at final time, tau I, or I mean tau f, right? Okay, now we know from classical mechanics that the system or a particle will always follow a particular path along which the action is minimum. Okay, so the next step would be now to compute the difference in action between the two paths, right? Okay, so what I'm going to do is I'm going to compute the difference in action, right? Okay, so I think the good idea would be to do that on the next page, right? Okay. So let me write it down mathematically. So my delta S, which is the difference in action, would be the time integral tau I to tau F d tau. Now again, I'm writing this integral or this action from the equation for action that we just described earlier, right? That is the proper time integral of my Lagrangian, right? So the Lagrangian would be the function of x mu plus some delta x mu, right? So like its original path plus some deviation, right? And likewise for the velocity. So its initial velocity plus the velocity with which it deviates from its path, right? Okay, so that's this. Now, because we're computing the difference, I would have negative, and over here I would have its initial Lagrangian, right? So again, from tau I to tau F d tau, and the Lagrangian would be a function over here of my simply x mu and x dot mu. Right. Now the next step from here is then the fact that we could expand this term or this Lagrangian function into the Lagrange sum of the Lagrangian of the original path and the deviation terms as well. So let's go ahead and do that. So I'm just going to say this delta S is equal to the integral tau I to tau F d tau, and over here what I would have is the Lagrangian as a function of x mu and x dot mu, right? Now plus the deviation terms would be added in as partial derivative with respect to x mu of my Lagrangian, right, times the delta x mu, right? So the deviation of the path, right, plus partial derivative with respect to x dot mu, which is the velocity component, right, of my Lagrangian, multiplied by the deviation velocity, right? So with what velocity it deviates from its path. Okay, and then we have this term over here. So let me just write it down as negative. We have this integral, right? So I'm just going to write the term inside the integral as L x mu x dot mu. Right, now let's close these brackets, making a mess. Yeah, now this is kind of neat. Okay, so if you see or look at this equation, you immediately realize that this term and this term just goes away, right? And so what you're left with from here is then the other terms. So let me write it down on the next page as my delta S, which is the action, is tau I tau F, this integral over d tau, and the other terms that survived were partial derivative with respect to x mu of my Lagrangian multiplied by the delta x mu plus partial derivative with respect to the deviation velocity, with respect to the velocity, right, of my Lagrangian, of course, and multiplied by the deviation velocity. Okay, let me close this, and all of this, what should it be equal to, right? So if you remember what we said earlier, that the system follows that particular path along which the action is minimum, and so to include, or to say be compatible with that statement, then this should be equal to 0, right? Okay, now if you look at this second term, right, this second term could be written as, or it actually comes from, say we have this total proper time derivative of my partial x dot mu of my Lagrangian multiplied by delta x mu. Right, now if you look at this and if you expand this, what do you get? Well, we get the proper total time derivative of my partial x dot mu of my Lagrangian multiplied by delta x mu plus, now this term, I would get this term over here, right? So what is that? That is simply partial x dot mu of my Lagrangian times delta x dot mu. Well, right, so this term over here is this term over here, right? And so now I can solve for this term, right? And then I would just simply substitute it into this equation over here, right? Okay, so let's go and write that down first. From this expression, what do you get? Well, we get partial x dot mu of my Lagrangian multiplied by the delta x dot mu is equal to, I'm going to rearrange the terms in this equation, right? And so what I get is the total time derivative, the proper time, of, one second, yeah, partial x dot mu of my Lagrangian multiplied by delta x mu, closing brackets, negative the total proper time derivative of my partial x dot mu of my Lagrangian, right, and multiplied by delta x mu. So all I have done is rearranged these terms so that I could have on the left hand side of my equality this expression, or this term right here, right? Now we have solved for this term in this expression, right? So let me just substitute this into this expression over here, right? So that's what I'm going to do in the next step. So let's go to the next page and substitute, right? So what will we have then? We would have delta s is equal to the integral from initial proper time to final proper time, d tau is the proper time, of my partial x mu of my Lagrangian times delta x mu plus d tau of my partial x dot mu of my Lagrangian multiplied by delta x mu, right? And let's close the bracket, and the next expression would be negative total proper time derivative of partial x dot mu of my Lagrangian, right, and multiplied by delta x mu. Right, so let's just close these curly brackets, and if you look at this equation over here, right, this second term in this expression or this equation will actually vanish, right? So that integral would be equal to 0. So what's that integral? That's tau I tau f of my d over d tau, that is of partial x dot mu of my Lagrangian times delta x mu. Right? Okay, so what would happen to this, let me write it, yeah, this. So this integral would equal to 0. So what you are left with then is then the fact that this goes to 0 and you're left with this term and this term, right? So let's go ahead and write it down. Actually, also let me mention the fact that we know that this delta s is equal to 0, right? So this whole expression is equal to 0. So the integral, everything that is inside the integral, if the whole integral is 0, everything inside the integral would evaluate to 0, and so what you would be left with are these two terms as I just mentioned, right? But also note that we would have you have this delta x mu and delta x mu as well, so we could just factor that out, and what you would be left with then is partial derivative with respect to x mu of your Lagrangian L minus the total proper time derivative of partial x dot mu of your Lagrangian L, right? And this is equal to 0. Now let me box this equation because this equation is important and it has a name, right? So this is the Euler Lagrangian for a relativistic particle, and for a relativistic system its evolution is described from the solutions to this equation, right? Okay, so we are essentially done with this video, but let's go ahead and quickly look at an example, right? Okay, so let me write it down over here, that example, right? So let's consider the kinetic term of a force-free Lagrangian. That means simply that there is no interaction term, right? And so consider that that Lagrangian is equal to 1/2 m eta mu times eta mu, right? So that's the contraction. Now if you recall the Euler Lagrangian, right, that we have actually just written above, so you don't have to recall, just look above, right? So we are going to use this and we are going to solve for the equation of motion, right? Okay, so note that we may write this Lagrangian over here as being equal to 1/2 m times g mu nu of my eta mu times eta nu. Right? Okay, now note that this first term of your Euler Lagrangian, that is partial x mu of L, right? So that's nothing but the partial derivative of your Lagrangian with respect to x mu, right? And so x mu is nothing but the position coordinate, right? And eta is, or eta mu or eta nu is the proper velocity coordinate, right? And so we don't have the position coordinate in the Lagrangian over here, so then this derivative would be 0, right? Now the next step would be to obviously compute this term over here, keeping in mind that we're doing it for this Lagrangian, right? Okay, so going to next page, I'll do it over here. You have to compute partial eta mu of my Lagrangian, right? Yeah. So if I compute this, what would this be, right? Keeping in mind that this is my Lagrangian. I'm sorry, we are using this Lagrangian, right? This one over here. Okay, so yeah, this is the Lagrangian, and so we have to compute this quantity. So let's do that. That would be then m over 2 times g mu nu partial derivative. So we're going to apply the, what you call, I think you say product rule, right? So we are going to do that. So eta mu, so this is partial derivative with respect to eta mu of eta mu times eta nu, and plus, like you would have in this product rule, right, g mu nu. Now we would have the derivative of the another term, right? So let me write down eta mu and the partial derivative with respect to eta mu of my eta nu, right? Yes, so that's it. Now further simplifying this expression, what do I get? I get m over 2 times, now if you look at this expression, these two things would just cancel out, right? Why? Well, because that is simply partial, it's partial over partial eta nu, and you have this eta nu, right? So they're the same things, right? So they would just go to 1, right? Okay, so let's get rid of this. So if those would cancel, then g mu nu on eta nu would, all it would do is it would replace your nu with mu and bring it down, right? So it would make it covariant, and so we would have eta mu, and look at this term over here, would you have plus. Now what would happen over here? Well, likewise your metric tensor would act on eta nu, eta mu, and it would bring down the mu and replace it with nu. So I would have eta nu multiplied by delta, because this thing can be written as delta nu mu, right? So this mixed tensor, right? Now this equation can then be further simplified as m over 2. If my mu and nu are equal, then this mixed tensor evaluates to positive 1, right? Okay, so then what I would have is m over 2 times eta nu plus eta nu. I'm sorry, I'm saying nu. What I mean is eta mu, right? And there are two funny words, right? And they sound pretty familiar or pretty similar, right? Okay, so now let me get rid of this. Yeah. So then if you look at this, your 2's will go away and you would be left with m times eta mu and yeah, so just give me a second. Yeah, so you would be left with m times eta mu, right? Because this expression would give you 2 times eta mu, and 2 would go away with this 2, right? Okay, so well, what is this equal to? This is equal to partial eta nu of the Lagrangian, right? And so now the Euler-Lagrangian or the Euler-Lagrange equation, which is this equation over here, right, the first equation in the box, what does that become? That now becomes, if you substitute the values, we found out that this expression over here evaluated to 0, and we just figured out what this would be. We just figured out this term, right? So that is m times eta mu, right? So we could write this equation now as 0 minus the total proper time derivative of m times eta mu, and this thing is of course equal to 0, and so what do you get is directly negative total proper time derivative of m times eta mu is equal to 0, right? So, and now if you find the solutions to this equation, they will then describe the evolution of such a system whose Lagrangian is written or defined as this, right? So this was just an example to make things a bit more clearer, and we are now done with the video. I hope you understood the idea of the Lagrangian in relativity, how do we go back to the classical Lagrangian, and likewise for the Hamiltonian. So the this is now the general usage or the general Lagrangian, right? And we can go from this relativistic Lagrangian to classical Lagrangian as well. Likewise for the Hamiltonian, right? Okay, so I'm done with this video. In the next video, hopefully, we would be looking at the covariant treatment of this relativistic Lagrange.